My name is Sara Jones. I'm a PhD candidate at the University of Arkansas working with Lance Miller. My research interest is in the area of commutative algebra and specifically Lubeznik numbers. In particular, my research is centered around taking a combinatorial approach to calculating Lubeznik numbers. First, let me give you some reasons we study Lubeznik numbers. Among many other uses, Lubeznik numbers are very beneficial in capturing connectivity information. For example, what we call the highest Lubeznik number computes the number of connected components in the Hochster-Hunecke graph. There is also a relationship between Lubeznik numbers and connectedness properties in the spectrum of a local ring. So to give you a concrete example, if you consider the union of two planes, the highest Lubeznik number in this case is 2. Because of this relationship with connectivity, it's not hard to see that in most cases, if the underlying structure associated to a ring is connected, then we have what we call a trivial Lubeznik table, in which the highest Lubeznik number is 1 and all others are 0. There are wide classes of rings that have trivial Lubeznik tables, including even Cohen-Macaulay square-free monomial ideals. There's been a lot of research devoted to simply determining when the Lubeznik table is trivial and when it's not. So what actually are Lubeznik numbers? In short, they are the Bass numbers of local cohomology modules. They can be computed in several ways. For example, if you are given a local ring R, admitting a surjection from a regular local ring S, where I is the kernel of the surjection, you can explicitly calculate the Lubeznik numbers of R as an X module using S and I. And it's not hard to show that this calculation is independent of the choice of S and I. In general, though, this process can be difficult to compute. However, in the case of square-free monomial ideals, this computation is much more tractable. So Montaigne and Yanagawa showed that in this case of square-free monomial ideals, you can compute Lubeznik numbers from the homology of the linear strands of the Alexander dual, where linear strands are simply a way of breaking up the free resolution. This has basically been the motivation behind my research. In particular, this theorem can be used to study edge ideals, which is what I enjoy studying. Edge ideals are square-free monomial ideals in a polynomial ring, but they're ones that can be built from a graph, and more specifically where the generators of the ideal correspond to edges in the graph. So the question I became interested in is, can you compute the Lubeznik numbers of edge ideals purely from combinatorial information found in the graph, which is where much of my research has been devoted. Not surprisingly, I have seen connectivity of the graph, such as the number of connected components, playing a role in the Lubeznik table of the edge ideal, but I've also observed other homological data from the graph manifest itself in the Lubeznik table as well. So knowing that the Lubeznik table can be computed using connectedness of the graph inspired another question. Can you split the Lubeznik table? In other words, can you compute the Lubeznik table of an edge ideal by recognizing it as a sum of Lubeznik tables of smaller ideals? Montaigne answered this question, but he did so for cover ideals in one result, and in another result for any square-free monomial ideal, but only where the summands of the Lubeznik table were representing ideals that were in disjoint sets of variables. My work on splittings has been dedicated to allowing for non-disjoint sets of variables, but specifically for edge ideals. Also, consequences of my work on splittings answers a question posed by Adam Van Tuyl. Specifically, this exploits that cover ideals are duals of edge ideals. He asked for natural Betti splittings of cover ideals, where Betti splittings are ways of breaking up the ideal so that its Betti numbers, which are the ranks of the term in the free resolution, can be given as a sum. And if you recall, Lubeznik numbers can be calculated using the homology of the linear strands of the dual of the edge ideal, which is the cover ideal, and so finding a Betti splitting of the cover ideal is where the heavy lifting of answering the original splitting question lies. So that's all I'll share for today, but I look forward to sharing more about my research with you all on Monday. I'll see you then.